video covers topic 2, characteristics of a graph, zeros, intercepts, extrema, continuity. Several ideas here to cover. First, we're going to go take a jog back to memory lane to determine f of a and when f of x equals a, back from Algebra 1. So let's jump over to the left-hand side of our notes. Remember, back in Algebra 1, we were asked to identify and find when f of 4 and for which x values f of x is equal to -1. Now, remember back in Algebra 1, these questions were really asking you, f of 4 meant when x was equal to 4, what was the y value? And we answered f of 4 is equal to, and we gave our x value as an answer. For which values of x is f of x equal to -1? What we really were doing here is we were actually giving you the y values and asking you for the x values. So we answered x is equal to, and we just put our answers in little curly brackets. So as an example, if I asked you to find g of 2, if this is the graph of g of x, and asked you to find g of 2, really what that means is when x is equal to 2, what is the y value? Well, if this is x equal to 2, we come down, we find the point on the graph, and that must mean it is equal to -2. We find the y coordinate that goes with the x coordinate that falls on the graph. Okay, for which values of x is g of x equal to 1? What's really happening here is I'm asking you when y is equal to 1. So here is my y value equal to 1. Well, we can think about this as if I were to shoot over and hit and intersect the graph. We intersect at 2 locations. What x values are those? We can see that occurs at about 3.5 and x is equal to 5. So we can have multiple x values here for when the y value is equal to 1. Okay, back to the other side. The main topic of today, just like we covered a moment ago, is about vocabulary, recognizing vocabulary terms that show up. We're going to start off by talking about 2 things we should already know, the x-intercept and the y-intercept. X-intercept is a point where the graph crosses the x-axis, and our points are listed as x, 0. Y-intercepts are the place where the graph crosses the y-axis, and they're listed as the point 0, y, whatever that number is going to be. Additionally, when we say x-intercept, these other terms, 0 of a function, root of an equation, and solution of an equation, all mean the same thing. So we'll see as we continue out the year. If I ask you for the x-intercept, the next line I may say, what's the root? Asking you about the same thing. Okay, what do those look like on the graph? Let's go ahead and mark them up on our graph. X-intercepts, we see that this is an x-intercept, x, 0. We see that here is an x-intercept. We see here is an x-intercept. And we can actually go ahead and put those values in as -4, 0, -1, 0, and 2, 0. For the y-intercept then, we can see that the graph crosses the y-intercept right here. 0, y. This case, we can say it's about 0, -1/2 would be my y-intercept looking on the graph. Okay, now on to 2 other terms we may or may not know. We did zeros and intercepts. Let's talk about extrema, or mins and maxes. Okay, so first and foremost, extrema or mins and maxes occur on what we call turning points. Turning points is just where the graph changes direction. You can think about it as either a smile or a frown. One of these 2 locations is a turning point in the graph. Either it changes directions. It goes from going down to going up to going down. So at these turning points, we label them not as smile and frown. We use them as either minimum or maximum. Now, there are different types of min and maximum. The first one we're talking about is relative, or sometimes called local. It is the smallest value in an open interval, or the largest value on an open interval. Now, what I mean by open interval is there are other values around it. It's actually going to look like a smile or a frown. We have a high point or a low point in a certain region. It doesn't need to be the biggest, just in the local region, it's going to be the biggest or smallest value. So, let's take a look at finding the local minimums in our graph. We see here, if I'm tracing along, here looks like a low point. So this is a relative or local minimum. It is the smallest point in this region. If I were to zoom in, it's not the smallest point overall, but in this general region, it is in fact the smallest point. All right, well, let's take a look. What's a relative or local max going to be? Well, here, this point right there is a relative max. It is the highest point in the region. And over here, we also have what we could call a relative max. They are the highest points in a region as we're going through. Okay? One thing to note about relative mins and relative maxes that's very important is that extrema, so relative mins or max, do not occur on the endpoints of a domain. They only occur in the interior. So going back to my graph, I did not label these 2 points. I did not label these 2 points as relative mins or relative maxes. Well, obviously they're not going to be maxes because they're not the highest, but I did not make them as relative mins. I can't see what's going on the other side of this point, and I can't see what's going on the other side of this point, so I can't actually say it is in fact a relative minimum. Okay? It has to actually be a smile or a frown. It has to see the change in direction from increasing to decreasing, decreasing to increasing in order for it to work. Okay? Very important point. Shows up on a couple test SAT questions trying to get you to mark those as relative mins when they are in fact not. Okay, they are points though, all right? So we do want to actually label them, and that actually goes down to the next 2 vocabulary terms is absolute min and absolute max. Absolute min and absolute max. Absolute minimum is the smallest value the function will ever take on, and the absolute maximum is the largest value that the function will ever take on. So it is in fact the highest and the lowest point on the graph over the entire domain. So if we look over to our graph once again, if I asked you what is in fact the highest point that we see, here this is in fact our absolute maximum, highest point over the domain. Here we have endpoints that are listed, so if this is another endpoint there, this is in fact going to be our absolute minimum point on the graph. Okay? We don't always have to have these. They don't always have to have an absolute max and absolute min. One little note is that they do not always appear on the graph. Sometimes there is no absolute maximum. Sometimes there is no absolute minimum. Okay? If that occurs, we just say our answer is none. Okay? Just think about normal quadratic. If I were to come over here and draw just a random graph and go like this, here we could say that, oh, I see that there is a relative min, and in fact it is in fact the absolute minimum as well. But as I try to come up here to mark down some type of absolute or relative maximum, the graph just continues on and on and on and forever in up and up and up. So in this case there is no absolute maximum, and we would just write none if that was it, or none on the absolute maximum point. Okay, don't always have to have them. Sometimes students fall into that trap. They just want to label something. Not always true. Okay, so jumping over to the left-hand side, I have 2 practice examples for you. Take a moment to see whether you can go ahead and answer these questions about these 2 graphs that are provided. I'll give you a moment or 2 to do that. Answer appears in 3, 2, 1. Go ahead and check your work. Okay, moving back to the Pride side, we have one other vocabulary section to cover, and that involves discontinuities. We started talking about these in class, but here it is officially. Discontinuity just means that there is a break or a hole in an otherwise smooth-looking graph. So usually graphs are nice and smooth, just like my example up here. Nice and smooth, no breaks, jumps, anything like that. Discontinuity is when the graph gets kind of broken up by one of these 3 options. The first option that we have is something called a point, or it's called a removable discontinuity. Basically what that means is the graph is kind of doing its thing, nice and fine, and all of a sudden there just seems to be like a pothole in the graph. And then it just continues going on and on and on forever in its opposite direction. Okay? These are both examples of point discontinuities or removable discontinuities. Right? In this case, the point, there is a hole and it's just completely gone. Right? There is no other one. Here, you could kind of see that the point actually dropped down. There's no difference between these 2 other than the fact that these are just both point or removable discontinuities. All right, next, jump. Jump sounds exactly like what we see here. The graph is kind of moving along, just doing its thing, and all of a sudden either jumps down and starts continuing on, or it just jumps up and starts continuing on. Okay, the graph just kind of does its thing, and all of a sudden just switches gears and starts somewhere else. Okay. Please note the difference between what we see happening here. This is a point, because the point just drops off. The graph just continues going in the same general direction, except one point is missing. Here, the graph is completely removed and starting off on a new location. Okay, very different. Sometimes students confuse these 2 because they see that there's a closed dot and an open dot. No, point, the graph just continues going on and only one point blinks out. Here, the graph completely restarts in a new location. Lastly, we have what is called infinite or asymptote. And I'm actually going to make a little note here. We're going to write the word vertical. Vertical obviously means up and down. So I'm going to draw there up and down. Anytime we have a vertical asymptote, we technically have an infinite or asymptotic discontinuity. Now, that doesn't matter whether the graph is going in the same direction on both sides or whether it's going in opposite directions like I've listed here. These are called infinite asymptotes. Okay? In terms of classifying them, we're going to go make sure we know these terms. The way that we identify them is we tell them where they are. So here I would say that there is a point or removable discontinuity at x is equal to 3, which is that value, x is equal to 3, and we see it at x is equal to 6, which is right there. For a jump, again, we just use the x values here. We see it at x is equal to -2. There is a jump discontinuity. Lastly, on our infinites, here we see at x is equal to 5, we see a infinite discontinuity, and here we see at x is equal to 3, another infinite discontinuity. Now, last thing to note on infinite discontinuities, you may have saw and may be wondering, what's going on with this? Horizontal asymptotes do not cause a discontinuity. So again, horizontal asymptotes do not cause a discontinuity.